Hello everyone. Today in this video we're going to talk about logic gates and how they combine together inside of a computer to make decisions. So we're going to look at what the different logic gates you're going to need to know are, what they actually mean, filling in truth tables, and actually building truth tables based on something called a logic circuit, which we'll all get into as the video goes on. Now in GCSE you're going to be looking at the sort of 6 main logic gates, but there are 3 that are more sort of obvious than the others. So these ones are worth writing down if you need to refer to your notes a little later on. Now an AND gate kind of looks like this, almost like the capital D at the end of AND there. What you do is you have 2 inputs that go into the AND gate on the left hand side, and then one output that comes out on the right. So what AND means is that both inputs, so you have your first input and your second input here, both of those have to be on. So the first and the second have to be on before the output is also on. So for example, if I had 0 and 1 here, well, 0 and, well, both of them have to be 1. So because this one's 0, the output would be 0 as well. If both of them are 1 though, then the output would be 1 as well, because 1 and 1 makes 1. OR gate looks kind of like that, where you have 2 inputs again and 1 output. But an OR gate, it will take either input. So as long as A or B is on, so your first input, your second input, as long as one of those is on, that's fine. The output will be 1 as well. If both of them are on though, then that's okay too, because either A or B is on, isn't it? And both of them are on, so either one of them is on too. So that would be fine for 1 as well. And we've got a NOT gate. Now a NOT gate's kind of a little bit different. Looks kind of like a triangle with a nose. The nose is relevant. We'll talk about that in a minute. But you only ever have 1 input going into a NOT gate and 1 output. So the NOT gate is exactly what it sounds like. If it's not 0, it's 1. If it's not 1, it's 0. So a NOT gate reverses anything that goes through it. So it's a 1, it's a 0. If it was a 0, it's a 1. Nice and straightforward. So, doing some truth tables then, using the information that we've just looked at. Now, you can see the circuits up here. If you didn't get them written down earlier, you can always pause the video previously or look at them on here, because they're kind of a lot cleaner on these diagrams than my scratchy writing. But let's focus on this AND gate for a second. And what this has to do is something called a truth table. Now, a truth table kind of looks like this. Well, the ones we're looking at shortly will be a little bit bigger. But just for this gate, the AND gate has a truth table that looks like that. Now, the way we've built that truth table up is we've said, well, we've got A, which is our first input, B, which is our second input, and out, which is kind of what's happening exactly at this point here. So the output of this gate would be there. So A and B, there's a way you can make sure you get every single possible combination, and that's the purpose of a truth table, to show every possible combination based on what is inputted and what will be output. So the combination you always do, you don't have to do this, but it's a good idea to get into the habit of saying, well, we start with 0, 1, then, 0, 0, then 0, 1, then 1, 0, then 1, 1. You'll notice I've got 0, 1, 0, 1 as a little pattern on the first, on the right hand side here, and then it doubles actually, so you've got 0, 0, 1, 1 on the left hand column. So that will give us 0, 1, 2 and 3 in binary, if we remember we have 2 and 1 across the top. So basically we've got every single combination. If you follow this pattern, you can't go wrong. And to be honest, whilst we're sat here, we may as well also pop it in this side as well. It's exactly the same. When you've only got 1 input though, it's just 0 and 1, because it would be the equivalent of writing this. Anyway, going back to our AND gate. Now, as we said earlier, A and B both have to be on for this to come on as well. So A and B are both 0 in the first instance, that would be a 0 as well. A is off, so that would then be a 0. B is off, so that's a 0. So A and B are both on here, so therefore that means this would be a 1 as well. A or B, again, you could label it your diagram if you want to. Now A or B, either A or B needs to be on, so that's not going to work for us. 0 and 0 is still 0. 0 and 1 here is 1 because B is on. A is on, so therefore this is 1 too. And then both of them are on at the bottom, so that's fine as well. And an OR gate, that's on as well. And as we know from earlier, a NOT gate reverses anything that goes through it. So if it's not 0, it's 1. If it's not 1, it's 0. You may wish to get those down in your notes for me for now, before you have a go at the next gates, just so you've got them all clear for yourself. And now there are 3 other gates to use, all kind of tangentially related to the ones we were just looking at. We've got something called a NAND gate, which is just a normal AND gate, but with a nose, as we were talking about earlier. So what this does is it's exactly the opposite of an AND gate. So if either of these are on, well, sorry, to clarify, in a normal AND gate, 1 and 1 would make 1. But because we've got the nose, so to speak, reversing anything that goes through it, 1 and 1 is actually 0. And the same applies for anything else. So 0 and 0 would obviously be 0 in a normal AND gate. Because of the nose, you reverse it. Okay, so 0 and 0 is actually 1 in a NAND gate, and the same applies for 0 and 1 too. That would be a 1, because normally this would be a 0 in a standard AND gate, and the nose reverses. Now, you can probably work out, a NOR gate is exactly the same as a NAND gate in concept. It's an OR gate, but reversed. So, if you had a 0 and a 1 here, that would normally be a 1 in an OR gate. Because of the nose, it's going to be a 0. The only instance where you get 1s out of a NOR gate is if 1 and 1, because that would normally be, my apologies, if you had 0 and 0, that would normally be 0 as well, so that will be 1 in a NOR gate, because that flips it. Now an XOR gate, is worth paying attention to. This one is your standard OR gate, or as close to where I can draw it. But then you put an extra line just here. Now that kind of still works the same, so you have your 2 inputs and 1 output. Now an XOR gate works like an OR gate, so 0 and 1 would normally be 1, but the X stands for exclusively. So if I was to put my output line back, thank you very much, if I was to put 1 and 1 here, normally that would be a 1 in an OR gate, but it's exclusively OR, so either A or B, not both. So 1 and 1 would be 0 in this instance, because A and B are on, which is not acceptable in an XOR gate. It has to be exclusively A or exclusively B. So this would be fine, but not both of them. And the truth cables, again, will go through the same motions of popping in the A's and the B's. It's always the same combination, just to make sure we don't mess it up like I just did there. You just go for 0, 1, 0, 1 like this, and then 0, 0, 1, 1. That gets our combinations. Again, assuming A and B and out, the same as last time. I'm not going to label them all up. A NAND gate, the best way of doing this, you could almost say, well, it's going to be, normally, it would be a 0 in an AND gate. Normally it would be a 0. Normally that would be a 0. Normally that would be a 1. And then you can reverse them all. So that would be a 0. That would be a 1. That would be a 1. That would be a 1. So then you can know, well, that's definitely what it would normally be as an AND gate. And then the nose reverses it. NOR gate, exactly the same. That would be normally a 0 and a 1 and a 1 and a 1. So we'll flip them. So that would be a 0, 0, 0 and a 1 as well. XOR gate, 0 and 0 is still 0. One of them still has to be on. But B is on here, A is on here, but they have to be on exclusively. So exclusively A or exclusively B, not if they're both on. So it looks like this. Those are all the gates you need to know for the GCSE, the 6 ones we've just talked about. So we're going to have a little bit of a practice with actually combining these together to a logic circuit. So there are 2 logic circuits in front of us right now. So we've got the simple one on the side, and then a more complicated one on the right here. Now, the way we would draw this table out, because there's no table at the moment, so the way you would draw it out is you'd notice, well, I've got A, B, here as my inputs. Now, you don't necessarily draw out because we've got 2 gates, haven't we? Now, the way I normally do it might be different for other people, but I normally do it is say, well, this is a process, isn't it? We're inputting here, and then we're processing the data here. So I'd be like, well, this is a P for process, and then I'd go alphabetically from there. So this is Q. So this is gate P, and this is gate Q. So I would be drawing 1, 2, 3, 4 columns going down. But you might be wondering, how do I know how many rows to draw? Well, the amount of rows you draw depends on how many inputs you have. So let me show you what I mean. Just undo that little doodles just here. Put those back up the top. P, Q. So how have I worked this out then? Well, I've got my A, B, P, and Q. Now, if I was doing this on my normal piece of paper or anything like that, I wouldn't draw the table first. What I would do is I would start with B and be like, well, that's 0, 1, 0, 1. And then with A, I would go 0, 0, 1, 1. As again, you do 0, 1, 0, 1 for your first input, and then you double up the number of zeros, double up the number of ones going down on the second. Therefore, now you can see with every possible combination, there are 4 combinations, so there should be 4 rows. That's how I do it. When we come to this one in a second, I'll explain exactly that in a little bit more detail. But what's P then? Now we know P is an AND gate. So another way you could write this is you could say, well, P is actually A and B. So A and B must both be on for P to be on as well. So we can see here that these are both zeros. Neither of these ones have A and B on, so these ones are going to be zeros. And the bottom one will be 1. Same as our truth table we did a minute ago. And we can look at Q as well. And we go, well, Q is a NOT gate, if I can find my pen. And what isn't it? Well, it's not P, because that was what was linking into it. P was linking in, so it's not P. So whatever P is, Q isn't. So if it's a 0, it's a 1. If it's a 0, it's a 1. If it's a 0, it's a 1. If it's a 1, it's a 0. Now that's complete now. We know that's all good. So this is when you've got 2 inputs, but what happens when you have 4? Well, I'd like to think it's fairly obvious we have to do A, B, C, D, then P, then I link this one as Q. Now the reason I do that is because this and this come before this gate. So you kind of work from top down, then left to right. So these ones first, then these ones, then this one, which would be R, which would obviously be P or Q, but we'll get there in a second. So if I build my table up, and for the sake of this video, I have put the zeros and ones in place. You can easily get into the habit of writing them down, but this pen's a little thick, so it's just worth making them clear for you. But at the top, we can still write our A, B, C, D, P, Q, R. Just going to label up the gates. We can probably work out what the inputs are. Now, P, again, is A and B. So A and B both need to be on, looking at these columns right now. Before we go any further, actually, you're probably wondering, how have I got this many zeros and ones? How did I know this was right? Well, you can see 0, 1 going down, the same pattern as I explained earlier. And then C is doubled up to 2 zeros, 2 ones, 2 zeros, 2 ones. B is 4 zeros, 4 ones, 4 zeros, 4 ones, and then A is 8 zeros and 8 ones. Definitely every single combination. So, again, so A and B both need to be on for P to be right, so these would all be zeros for now. And the bottom ones, you can see we've both got ones and ones here, so we'll put some ones in here as well. That's definitely accurate. And Q is the same. Q is C and D, but the way this looks is going to be different, because that's 0, that's 0, that's 0, and that's 1. If you notice, that pattern actually continues, so I'll just quickly whip those in. Then R. Well, R is an OR gate, and you could say that R is P or Q. So P or Q means as long as there's a 1 in either of these columns, we're good to put a 1 in the right-hand side into the R as well. The bottom ones are all going to be 1s, because we can see there's 1s all through here, as well as the ones we just noticed. So there we go. That's creating two truth tables based on the logic circuit we've got underneath. So if you want to take a few minutes now to A, draw out your own tables, and then B, complete them based on the inputs and the gates that we've got in these 2 diagrams. You can pause the video now if you want to do it without help of the tables. Or you can pause it at this point if you want the tables to help you. But it would be worth getting into the habit of labeling those inputs and those gates. We'll go through the feedback shortly. If you want to pause the video now. Okay, so A, B, C, and D are always the same. And we've got on the P, Q, and R, similar to the last circuit we just did. Let's label the power diagram here as well. Okay, so A or B, because this is an OR gate, isn't it? A or B. So we've got anything which has a 0 or any 1s in this entire column would mean that we have a 1 in P. So actually every single one of these underneath the first 4 is going to be a 1. And C or D means any of these with a 1 in. So the pattern's going to be similar from the first 4. There we go. And then R. R, if you remember, we can see that little line. That is exclusively OR. So P XOR Q. So these would be fine. I made a mistake. Whoops. So this one's a Q here, so that one needs to be a 1 too. 1, 1, 1. At this point we halt. We go P and Q are both on. So that's not okay. We need one or the other, not both. So that's fine. These aren't. That's fine. These aren't. We should have 6. There we go. So we can see that's nice and clear. Those ones just there. So that's all good. That's all fine. We can give a big old tick for that one. Again, this one. Now we've got 3 inputs this time. No real differences the way the methodology goes. You can see I've got the 3 columns up here for A, B, and C. And we use the same method of working out how many rows we need. So remembering that method, it's always worth knowing. And then we've got P, Q, and R again. Exactly the same. Now P is A or B again, so we can follow the same as what we did earlier. As long as ones are in either, we're good. Q. Now Q is not C. So whatever C is, Q isn't. So we'll just reverse C. Then R is P and Q. So P and Q. So that means that both of these need to be 1s. And only those 3 are. And there you have it. That one's all good too. So the things you need to remember when it comes to doing binary logic gates, you've got to remember your gates. There are 6 you need to be aware of, okay? And if you look, we don't actually have any NAND or NOR gates in these particular examples, but look for your noses. The noses will reverse, hence the NOT gate here reversing any inputs of C. So that's important. Remembering our XOR and our OR gates are different. OR is very inclusive, takes everything. R is XOR is exclusive, as you can see. Does not take both of these inputs at the same time. But there you have it. If you have any questions, as I say, leave comments down below and we'll get to answer as many as we can. Thank you for watching.